Hello, I'm Kanta Kaneda from Keio University, Japan. In this presentation, I would like to introduce our paper titled Flare Transformer, Solar Flare Prediction Using Magnetograms and Sunspot Physical Features. First, I would like to introduce the background of this study. This video shows a solar flare filmed by NASA. Solar flares are large explosions that occur on the surface of the sun, producing shock waves and magnetic storms. Because large solar flares cause disasters such as radio blackouts, national agencies such as NOAA in the United States monitor and forecast flares every day. In fact, solar flares have caused extensive damage to the social infrastructures and space industry in the past. This table shows some of the disasters caused by solar flares. For example, solar flares caused a major power outage in Canada in 1989, and just this past February, SpaceX announced that 40 of its 49 satellites had been disabled by a magnetic storm caused by a solar flare. In addition, an insurance company in Switzerland estimated that the economic loss from a largest solar flare would be about $160 billion, even if limited to the North America region. Like this, solar flares can cause significant damage, but these damages can be minimized by taking countermeasures in advance. Therefore, the technology to predict the occurrence of solar flares in advance is extremely important. Next, this slide introduces related research concerning time series forecasting and solar flare prediction, because they are relevant to our task. Research on time series forecasting began with classical statistical methods such as ARIMA, and recently, methods using recurrent neural networks such as DeepAR, and models using transformer attention mechanisms such as Informer has been proposed. Next, existing research in the field of solar flare prediction includes the method of Park et al. And DEFN. Park et al.'s method takes solar images as input and predicts solar flares using CNNs. The DEFN model uses sunspot level physical features as input to predict solar flares. However, the performance of existing solar flare prediction models still have room for improvement, as existing solar flare prediction models have not been able to outperform expert predictions. Next, this slide introduces the problem statement. In this paper, we focus on the task of predicting the class of the largest solar flare that will occur within 24 hours from time t. The input are line-of-sight magnetograms and physical features. The magnetograms shows the entire image of the sun, as shown on the right, with active regions highlighted in black and white. Physical features are sunspot level physical features extracted from solar images and containing time series information. The output is the solar flare class. There are 4 classes of solar flares, X, M, C, and O, and as shown in this table, X-class flares occur less frequently, but cause more damage when they do occur. This graph shows the breakdown of solar flare classes that occurred from 2010 to 2017. X-class flares, which have the potential to cause significant damage, comprise about 1% of all flares, while O-class flares, which are smaller in scale, comprise about 59% of all flares. As this graph shows, the solar flare prediction task is characterized by an unbalanced distribution of classes. When dealing with forecasts of such phenomena, it would be inappropriate to evaluate the occurrence of each class equally. Therefore, rather than general classification accuracy, it is important to evaluate this task using GMGS, TSS, and BSS, which are standard metrics in this field. Next, I will introduce the novelty of this paper. In this paper, we propose the flare transformer, which handles a time series of images and physical features to produce accurate and reliable solar flare predictions. The novelty of this paper is the following 4 points. The first is the introduction of the magnetogram module, which handles magnetograms. The second is the introduction of the sunspot feature module, which handles sunspot level physical features. The third is the introduction of a transformer attention mechanism in the aforementioned magnetogram module and sunspot feature module. And the fourth is the introduction of new GMGS and BSS losses to balance the standard metrics of solar flare prediction. Flare transformer consists of two main modules, magnetogram module and sunspot feature module. Each module first extracts features from each input, and then temporal relationships are modeled by NV or NF transformer layers. This slide shows the more detailed structure of the flare transformer. First, the input to the flare transformer consists of magnetograms and physical features from time t minus k plus 1 to t. Magnetograms are resized to 512 times 512 pixels, and 19 physical features are obtained from images of sunspot regions. The output is a four-dimensional vector that denotes the predicted probabilities of each flare class. We use the following loss function, which is a weighted sum of cross-entropy loss, BSS loss, and GMGS loss. The cross-entropy loss is given by the following equation, which calculates the cross-entropy between the predicted label and the ground truth label. The BSS loss is given by the following equation. Since the metric BSS is differentiable and could be used as a loss directly, we have introduced a loss function that directly maximizes the BSS. The GMGS loss is given by the following equation, where the S here is the GMGS score matrix used in the metric GMGS. The GMGS score matrix is a 4x4 matrix corresponding to each class. This is an example of a GMGS score matrix. For example, if an X-class flare is incorrectly underpredicted as an O-class flare, a penalty weight is given to the score. On the other hand, if a C-class flare is correctly predicted as a C-class flare, the evaluation is given a weight of, for example, 0.5. Furthermore, if an X-class flare is correctly predicted as an X-class flare, it is given a higher evaluation weight than if the C-class flare is properly predicted, because the prediction of X-class flare is more important. This GMGS score matrix allows for a smooth learning in this task, which has an imbalance of importance among the classes. Next, I will introduce the experimental setting. We use a dataset that contains more than 60,000 samples, covering from June 2010 to December 2017. A sample consists of a line-of-sight magnetogram and 19 types of physical features. We divided the training and test sets based on time series cross-validation, which is a standard method used in time series forecasting tasks. The breakdown of the divided sets are shown in this table. Next shown is the quantitative results. The DEFN and DEFN-R models, which only take physical features as input, were used as the baseline methods. We validated the models by GMGS, TSS, and BSS. Please note that for TSS and BSS, we calculated the scores after the output has been categorized as either greater or smaller than M-class. The table shows that the flare transformer model outperformed the baseline methods. Detailed comparison on DFN-R and flare transformer shows that flare transformer was 0.2 points better in GMGS, 0.25 points better in TSS, and 0.04 points better in BSS. These results indicate that the proposed method achieves better forecasting performance than the baseline methods. In addition, the bottom row of this table shows the scores for predictions made by human experts. This table indicates that the flare transformer gives better prediction than can be achieved by human experts in terms of GMGS and TSS. Next, I will introduce ablation studies. In the first condition, we conducted an experiment using only magnetograms as input. The results showed a significant decrease in scores as shown here. This indicates that the introduction of the sunspot feature module to handle both images and physical features was beneficial to the performance. As a next condition, we conducted experiments by increasing or decreasing the number of transformer layers in the sunspot feature module or the magnetogram module. The scores of each metric fluctuated slightly. We selected ablation D as a proposed model because it has the best balance of scores among ablation B to ablation D. For error analysis, we defined GMGS influence as shown in this equation, which measures the impact of failure samples on GMGS. This graph shows that the main bottleneck is a misprediction of X-class flares for M-class flares for the test set. In future research, we hope to further improve the performance by alleviating this bottleneck. In conclusion, we propose the flare transformer, a solar flare prediction model which handles heterogeneous data, which is magnetograms and physical features. Flare transformer gives better predictions than can be achieved by human experts in terms of GMGS and TSS, which are standard metrics in the field of solar flare prediction. Thank you for listening.